Hello.
Hello.
Hi, Nicholas. Okay. Why don't we get started? And then as people come in, we can discuss. So as a reminder, we're planning to record this video and share on YouTube. So if you have concern there, let us know before we push it out after the meeting. That's the first thing. The second is we're trying to follow this format of sharing the presentation prior to the meeting. And so I think everybody did a good job today of posting the slides on the discussion forum. So our process with Anna has been we call for the meeting, we discuss it the week before, agree on the agenda, and then create the thread, and then people can put in their presentation. And we expect more people to read those PowerPoint prior to the meeting, so then we can have an in-depth discussion during the meeting. Okay, so today the agenda is a couple things. So the first is Nicolas is going to present some analysis on SLAP2 data that he has done. I think Sarah also was planning to present, and so we're going to have this two presentation. And then I was planning to present different variants of the experimental design that we have conducted. And the intent today is to discuss at the end those variants, leveraging the insight from the analysis that has been done so far. And I know also Lucas has done some statistical analysis that he just posted. So maybe we might discuss that as we discuss the stimulus design. Okay, so that should fill the hour quite extensively. So why don't we get started? Nicholas, do you want to share your screen?
Yes, I can share my screen and get started. So just to preface, I engaged in more of a population level analysis for this meeting. I think that there are a few problems with a population level analysis. I think once we have control trials that I think that'll enable a more robust population level analysis. So I just wanted to preface with that caveat. In any case, this is how I pre-processed the data prior to my analysis, where I made use of the data that has been normalized by the baseline f of 0, labeled DFF in the data set itself. In addition to that, I selected ROIs since I was interested in how it is that each ROI's orientation tuning preference changed after the presentation of the oddball block. So I calculated the tuning spread per ROI. That just means that for each peristimulus window, for every ROI, I calculated the maximum and minimum value. I got the average, maximum, and minimum value, and I retained those ROIs that were in the top 25% of that tuning spread distribution. I go into a little bit more detail about exactly how I do this in my write-up in the discussion thread. So if you're interested in more details about this, you can refer to that. In addition to that, I performed ROI-wise min-max scaling. That just means that I rescaled every orientation tuning vector to between 0 and 1 per ROI. The reason I did that was that I wanted to address the problem of photo bleaching, since it seemed like if I were to look at amplitude, photo bleaching could interfere substantially with that analysis, because you would expect photo bleaching to decrease the average amplitude of the signal that we compute using SLAC 2. So rather than look at amplitude, I instead looked at the shape of the ROI tuning vector. So for instance, if one ROI was more or less tuned to 45 degrees over 90 degrees, regardless of its absolute responsiveness to those respective orientations. So that's a significant limitation of this approach as well. So I computed some radar plots to look at how the orientation tuning of each ROI changes after the presentation of the odd block. Now, what's important is that what we're seeing here has already been normalized using the pre-processing pipeline discussed in the previous slide. And what I noticed here is that certain ROIs seem to be tuned to multiple stimuli. And when, after the presentation of the odd block, these ROIs seem to change their tuning to multiple stimuli. Now, it is the case that certain of these ROIs seem to have just one dominant tuning. For instance, ROI 4 seems to have just one dominant tuning to 23. It retains that tuning after the odd block. We see something similar with ROI 0, where it has one dominant tuning and it changes its dominant tuning to something else entirely after the presentation of the odd block. So I think that there are different ROIs that exhibit one clear dominant tuning, but there are other ROIs that exhibit multiple tunings. So what I wanted to see was, after the presentation of the odd block, did the orientation tuning vectors of these different ROIs change all, by and large, in one toward single orientations, or did they exhibit patterns of change that changed multiple orientation preferences for each ROI? So to look at that question, I decided to make use of PCA, where I computed the cross-covariance matrix between the pre and the post block. I discussed this in detail.
Nicholas?
Oh, yes.
Sorry, my microphone didn't work. One question to the previous plot, if you could go back. Yeah, so what's going on with the orientations in this plot? And because, so as far as I understood, it's the degrees on the radial, on the angle.
That's right. Yes. Yes. Yeah.
But it's like, is it in steps of 23? Sometimes it doesn't seem to
yes,
play
yes.
out.
That's a problem with this plot. Yeah, you're right. There's this. Usually, it goes in. It increases in even increments, but at 157 and 158, they increase by 1.
I think what could be going wrong is that what is given is the direction, which is between 0 and 360. But these plots might be using so there might be a computation that transfers this to orientation angles. And in which sense, probably you have some line in the code that divides by 2, and then you end up with, rounding error, one giving you 157, 158. So I think at some point, I just make sure in the analysis that it's the direction angles and it's not, because I had the same issue when I was using
I believe isn't 157 and 158, aren't those are you saying that maybe I computed the conversion of radians to degrees incorrectly, and that's why I'm getting 157?
I think it's computing direction orientation to orientation angle, because orientation is only between 0 and 180. And I think you might be using orientations, whereas the actual data provide directions. I don't know.
I'll have to check.
I realized that Gemini smuggled that in a plotting script that I tried to use. Maybe that's what's going on.
Yeah, if you're using my code, there might a bug in that. That might be exactly a bug that I put in my code of the adaptation tuning. So.
Okay, I'll have to check that. By directions, as far as I saw when I was looking at the most recent data set, I saw the visual gratings having orientations, but you're referring to directions. Are we speaking about the same thing?
Yeah, that's why I'm nervous. I didn't realize that those are directions. So technically we could look at both, right? So these neurons could be direction selective. They could also just be orientation selective. In that case, whether something is moving up or down shouldn't matter. So both might actually be interesting data points, given that this is V1.
I see. So this is looking at orientation. I didn't look at direction, unless something was mislabeled. But this should be.
The issue with orientation is you only get 180 degrees. So yeah, I didn't think that through when I started writing that code. So the direction plot would give you 360.
I see. Yeah, I need to change these plots so that, yeah, these plots they're misleading. They give the impression of 360 degrees. I need to change them to 180.
Can I ask another question real quick? So the ROIs, are those the ROIs of the polar plots or of the time series? So not ROI, PCA, the PCAs. Are these the PCs of the time series of shapes or of the shapes of the polar plots?
So you're referring to the later PCA analysis, or you're referring to these radar plots?
The PCAs that you computed. Did you do them on the tuning plots or on the response time series?
I did them on, if I'm understanding you correctly, I did them on the tuning plots. So the covariance matrix, the rows refer to orientation degrees and the columns also refer to orientation degrees.
Okay, that's interesting because a lot of this manifold stuff that relies on PCA, they usually do the shape of the response time series, right? So this is a different manifold then. This is a manifold in the tuning space, not in the response space. Okay, thank you.
It's in the tuning space, exactly. And it's the cross covariance matrix between the orientation tuning vectors of the pre-block, the pre-orientation tuning block, and the post-orientation tuning block. Yeah. So then the cross covariance matrix, yeah, the rows would correspond to the average. I wouldn't say the average, but the rows would correspond to the pre-orientation tunings, the columns to the post-orientation tunings. In any case, so I wanted to answer these questions. When we're looking at orientation tunings in this PCA space, are we going to see one dominant covariance mode where we see just one shift in variance across these ROIs towards, say, the 45 orientation, which is our deviant stimuli, or the 90 degree, or the 0 degree? That's what I wanted to see in the covariance modes of this cross covariance matrix after performing this PCA. Alternatively, are we going to see, in the covariance modes, are we going to see changes or variance along multiple orientations and not just along one orientation? For instance, the deviant orientation. So those are the questions I wanted to answer. So I computed these summary plots, these PCA summary plots for, I don't have the session, I don't have the data set name, I'll include that. But this is just for one data set, and these are for DMD1 and DMD2 respectively. These were computed separately for DMD1 and DMD2 respectively on the cross-covariance matrix. And as you can see here, we're not really seeing a dominant, a covariance mode that is focused on just one orientation degree. We're not seeing, for instance, a covariance mode with a dominant, let's call it energy on, say, the 90-degree stimulus or the 0-degree stimulus or the 45-degree stimulus. Rather, we're seeing, with respect to these big population-wide changes, we're seeing changes across multiple orientations, some of which are, you would interpret as going in separate directions. Any case, so I wanted to provide another visualization that could maybe help with the interpretation of the PC loadings of the previous plot. So this is just a plot that is done to help, in that interpretation, where I take these PC components and I reconstruct the cross-covariance matrix using each of these PC components. So each of these plots are a rank 1 reconstruction of the cross-covariance matrix using the PC component labeled above. And as we see here, there seems to be some pattern emerging where this will all become a little bit clearer in some later scatter plots that I will show, but how you would interpret this is that if the ROI's orientation tuning is, for instance, high with respect to 90 degrees, its preference for the 90-degree stimulation, then we would expect its orientation tuning after the presentation of the odd block to we would expect it to have less of a preference for the 0-degree stimulation after the presentation of the odd block. That'll become clearer with these scatter plots that I present, where what I do here is I take the first two PC components and I reconstruct the data using those first two PC components. And as you can see here, the x-axis refers to the preference the preference of these ROIs, each dot corresponds to an ROI, for, say, the 90-degree stimulus. So that if it didn't have a very big preference for the 90-degree stimulus in the pre-block, after the presentation of the odd block, it would have a higher preference for the 0-degree stimulus. Similarly, if it had a very big preference for the 90-degree stimulus in the pre-block, it would have a very big preference for the 90-degree stimulus in the post-block. So I thought that was a interesting pattern, but whether or not this indicates preferential tuning for the 90-degree or 45-degree tuning, I don't think we can say that at this point, because we really need to, I think, compare this to a control trial. So these are just speculations that I'm giving at the moment. But in any case, I did the same for the 0 degrees. I plotted a similar visualization for the 0-degree plot, where the x-axis again refers to the preference of these ROIs for the 0-degree stimulus in the pre-tuning block. So as we can see, there seems to be a pattern that's evident. But again, the interpretation of the pattern may be difficult without having some control to compare it against.
Nicholas?
Yes.
Would you see this same, if you were not going to run this through PC and just plot the pre and post, would you see anything like this?
No, I see, I can actually show you the visualization on my computer to show you what it would look like without the PC reconstruction. So I'll share my screen.
And then another question I wrote on the chat. So how long is in between oddballs until the post epoch?
I think, so how long is the time between the pre-block?
Yeah, I'm just curious because if you're thinking that the oddball is...
I think, can Jerome, do you have a...
Every oddball is presented about 10 to 15 seconds. And then the whole oddball block is 35 minutes long, maybe a little longer. And then the pre and post are 5 or 6 minutes long.
Right, so we're thinking that within 35 minutes, we might be changing the tuning.
That's the current play of the task, yeah.
I mean, and is there anything else in the literature that says something this might happen?
Fast response?
Yeah, no, forget about that. That oddballs can change the orientation tuning. Is that a thing in the literature?
It's not necessarily the oddball that is changing the tuning. It could be the repetitive presentation of the drifting grading.
Right. So then we don't really know if this is
1 hour experiments of gradings. Sorry,
Yeah, please.
I'm gonna have to join. I joined from my remote computer by accident. I'll just share Mada's analysis of some recent experiments. Does that make sense?
Sure. Just one thing to make sure we're talking about the same thing. So we are not directly looking at oddball happens now. What happens on the immediately following stimulus? So we are just looking at pre-post. So this could not be necessarily due to oddballs, as you just pointed, Jerome. This could be due, right? Okay.
Can I share?
Sure. Yeah. Go ahead.
So last week we just presented the stimuli for an hour and looked at the tuning of, this is calcium in the neuron, and then these are synapses. The 3 colors are 20-minute blocks. So we haven't done any detailed analysis of this, but the synapses are behaving. I'm just scrolling through synapses. The synapses are behaving basically exactly the same through all 3 blocks. Each color is a different block.
So this was tuning block 1 and then constantly, or you have a gray?
So these are the stimuli that so we use Mada's stimuli rather than your stimuli. So these are longer stimuli, so you can actually see the phase response. So these are gradings to 8 different orientation and then a flank omission. They're just shown repeatedly for over an hour.
Okay.
And we sort of split it into 20-minute blocks.
But shuffled.
Shuffled on every trial. But the point is that basically every synapse, there's no just ongoing plasticity from showing the stimuli repeatedly in terms of the average response.
When it's shuffled.
So that might provide some context for the changes that you're seeing here, because if you're seeing a lot of changes, it's inconsistent with this, where we show a very similar stimulus, it's just a little bit longer, and see basically no plasticity whatsoever. I mean, you can look through all the synapses. I'm just scrolling through synapses. We basically don't see any plasticity.
Okay.
So what does shuffled mean? I don't understand. Can we clarify the shuffle of the paradigm here compared to the standard oddball presentation?
So here there's no oddballs, and it's just the order of the stimuli in every block of 9 is randomized.
Okay, but the equal number of representation for each orientation, essentially.
Yeah, and every block of 9.
Yeah. Okay. Yeah.
Can we keep this discussion for the end? I want to make sure that Sarah has time to present.
Yeah. Sorry, go ahead, please.
Yes, I think it's great content. Nicholas, do you have more?
I think my presentation is. I think we're at the end. Yeah, that's the end. That's the end of my presentation.
Okay, so you're seeing hints of changes of tuning in groups of ROI, in single ROIs, of group ROIs, single ROIs, and to see that you had to weight multiple orientation together. Is that right?
So, so what we're seeing is we're seeing a pattern where if, depending on the preference of the ROI in the pre-tuning block, that impacts its change of preference in the post-tuning block.
Okay. That would make sense.
That's the takeaway. That if, say, it tends to prefer the 0 degree stimulus in the pre-block, it will, after the presentation of the odd block, it's not going to be preferentially tuned to the 90 degree stimulus.
Okay, that makes sense. So it's sort of reinforcing the 0 degree.
Yeah, and what I also find interesting about some of these figures is particularly this one, where we see across DMD1 and DMD2 in the first principal component a similar PC component, where we see a similar pattern of a similar direction in the PC space with respect to the first PC component for DMD1 and DMD2.
And is that something that you've seen across multiple of the experiments we've looked at, or is that a single one?
I haven't looked at the other experiments yet.
Okay.
But I'll verify.
I'm a little concerned with just the feedback on controls, like, because when you do this higher order analysis, you can pick up structure because you're sort of biasing towards picking it up, and so I will have to think carefully about shuffle control here. I'm not sure what is the right way to do it, but
what do you mean by shuffle control in this case?
When you do PCA, you're gonna select subdimensions, and then there's likely going to be structure in those dimensions because you're forcing it. And so I'm just
true.
I'm just sort of being mindful of making sure what you see here is not due to that process.
I wonder if having I saw some of your one of the images you posted to the discussion thread of a proposed experimental design.
Yes.
Where you don't have an odd block between the orientation tuning blocks.
Yes.
I think if we were to run, say, a similar analysis on a control experiment like that and compare that to
That's
one, right. I think that comparison could reveal whether or not the structure we're seeing is due to the odd block or is due to something else.
That's right. Okay.
Just a quick question. So first of all, great job. I think this is a super interesting analysis and result. This is reminiscent of representational drift. Is that correct?
Can you repeat that question?
So I'm wondering if this is reminiscent of representational drift. So in a matter, if we find the same result, even if there's no distinct effect of the oddball block, it's still interesting, right? And so I'm wondering how similar this might be to what others have found as representation of drift, but now it's on the synaptic level. I mean, it seems interesting no matter what.
And so it's almost as if the pre-tuning, like what its tuning originally was, biases where its tuning drifts to, if indeed the odd block is not responsible for this. Maybe so that if it's tuned strongly towards the 90 degree, it may drift in the direction of 90 degrees. If it's tuned strongly in 90 degrees, it's not going to drift toward any strong preferential tuning with respect to 112 or 113 or some of these other degrees. I think what's missing from this analysis is looking at, for an individual ROI, how are they changing their tuning across these different dimensions, given that, say, for instance, they're strongly tuned to 90 degrees. I didn't include color coding for the different ROIs here because it would have cluttered the plot significantly, but I think that can maybe address the question you're bringing up, that with respect to a single ROI, if it's strongly preferentially tuned to 90 degrees, how will its tuning change with respect to all these other orientations, whether because of the odd block or not? Yeah.
I think, Alex, your point can also be looked at with different controls. I think one thing that Casper just showed earlier, where or doing orientation continuously and seeing how stable this is, I feel like there are several ways to address whether the audible block is triggering learning or it's just a natural process. Yeah.
I think even if it's a natural process, this seems a first and quite interesting. I think people have shown representation drift and spiking responses, but so early on in V1 with synapses, that's quite striking, because I think that the word on the street would be that this shouldn't change much. This is such a robust mechanistic system, especially early on in the visual system. I think this is surprising no matter what. The number one critique I can see is that we're prone to noise, right? So if you look at the tuning curves themselves, they have quite a bit error bars. So one critique could be, yeah, you know, you're doing two small number samples, and of course you might see some difference, but that's just noise. And I don't know how to deal with this problem other than to look at more sessions.
I feel like I think that's a good proxy for Sarah's analysis, because I think she was doing more direct, right?
Yeah, sure. Do you want me to share the screen?
Please.
Sorry, can't see my screen. It's great.
Nicholas, would you mind muting yourself while Sarah presents? There's some background noise, I believe, from your microphone.
Interesting. I can't see my presentation. That's interesting. That's a new one. Wow. Does this work? Okay, got it. Okay. Yeah, so what I've done is related to what Nicholas just presented, but I would say it's a bit more, maybe a bit more old school. And so I basically went down to the individual ROI level and just tried to understand what are the orientation tuning properties in terms of the orientation preference and the orientation selectivity index, also classic, essentially preferred versus orthogonal. And so the way I've done it is identify the blocks in a similar way that we discussed before. So we have the blue block, which is tuning block 1, and then the green block, which is tuning block 2. And in these blocks, I basically, for each ROI, calculated the orientation tuning curve which essentially results in traces like this. And I also had the issue with the 112, 113 degree and 157 and 58. And I tried to correct for it because I thought it was a rounding mistake. And so I pulled them and basically have a range from 0 to 180 right now. And I would say the gist of looking at basically all the hundreds of RIs that we have at the moment is that in principle, overall, the tuning itself for the majority of neurons doesn't change. But one thing that changes quite frequently in the majority of RIs, is that the response strength of delta F to delta F over F for the block 2 is almost always smaller than the response amplitude you have in the block 1. And the way you can see this here is because I basically visualized differently compared to Nicholas. So he basically peak normalized the responses for each block individually because he wanted to see the actual tuning range. And I peak normalized it to the maximum response across the 2 blocks for each ROI. And so I think overall, what I would call this is a very marked gain modulation of the synaptic strength that you see. That is not necessarily reflecting a tuning specific change, but an overall change in the, let's say, activation of these synaptic inputs in block 2. And when you look at the orientation selectivity values, you can kind of get a sense of what Caspar just mentioned. So a lot of these OSIs are very similar in block 1 and block 2. There's some, hunch that some of these RIs might be subject to changes in tuning, but it's not that it's the majority of RIs for sure. And so I basically went through all the 3 sessions that we have and generated these plots to kind of get a sense for this, also get a sense of like the tuning depth overall over the RIs. And you basically can summarize this quite easily by just looking at scatter graphs like this, which basically relate the orientation selectivity index for block 1 versus block 2 as a function of which depth are we imaging basically for the different RIs. And what you can see is that, there's a lot of RIs which kind of live around the unity line. And so like overall, clearly it's not like a massive change, but there are some RIs which are really dramatically changed that have initially very high selectivity and lose the selectivity to a large extent. And then there's also a small set of RIs which initially doesn't have much selectivity, but it gains it throughout that, exposure to this standard oddball paradigm. And so the next question, yeah.
I'm just sorry. I want to bridge with what Nicholas just presented. Does it align with what Isho, or is the point of alignment here is that you see a decrease tuning in cells that were not like because Nicholas said a subset that were tuned to the 90 degrees see a change and some do not, and so is that something that you corroborate or?
For some RIs, I would say yes, right? Because there's some which have a very strong orientation selectivity index. I just don't know whether these are, at this stage, I don't know what they're really preferring in terms of the orientation, right? So it would be a bit more agnostic at this stage and not say it's tied to a particular orientation preference. I would just say it's the tuning depth overall that's changed, right? Either they start responding to orientations that they didn't respond initially to, or they actually lose the response to the initial preferred orientation. That's something I don't know yet at this stage.
So you could bridge with Nicholas' analysis by color coding here the dots depending on the initial orientation, right? Is that what?
Yeah. I tried something like this, but here it's a bit cryptic in a sense that I plot the preferred orientation. This is just the peak response, right? It's really like the simplest metric we have, the orientation preference in block 1 versus block 2. And you see, there's lots of RIs which are not on the diagonal, so they change. But to what extent they change kind of is a range, right? So the color code here is basically reflecting as a function of getting more intensely red, a stronger change in the angular preference for the given ROIs. And so some change really dramatically, but a lot of them that change maybe by 10, 20 degree, right? So you wouldn't necessarily call it a massive reorganization of the preferred orientation. And I think a better way to visualize this is kind of the last two types of graphs that are generated. So this is just looking at the orientation selectivity itself, and where do these ROIs live along the dendrite. And so you kind of get two things as a sense, right? So you see that overall there's a prevalence of green, which means a lot of these ROIs are kind of selective, but at a lower selectivity range. And in the last column is basically plotted a change in the orientation selectivity. And so you see you get a few which increase, a few which decrease, but a lot of them say actually gray, which is probably related to what Kasper was saying. And then the final thing you can do with this kind of visualization is basically related to the preferred orientation. And then you see also that a lot of these ROIs are gray in the sense that they don't change the preferred orientation. But there's almost like some hot spots where there's, a really striking change in the orientation preference, where maybe it's kind of a convergence of inputs that changes, as a function of the experience. And that's overall basically true throughout the 3 sessions that we have, I would say. And I would say, the most striking thing to me is really that this response strength is something that seems really consistent. So here we have a different session. We picked a lot of these ROIs which don't have a change in strength, but the last one is, a striking one, which basically just has a massive gain modulation, basically. And that's a feature, I think, that we can more easily pick out with this type of analysis compared to the other analysis we discussed before, which I think is interesting from the perspective of, what does it mean to have experience-dependent plasticity, right? So why is there a change in the overall strength of activation, not necessarily the tuning? And so it could be some form of adaptation, or it could be some kind of new modulatory effect. It could be some state-dependent change. But I think it's something that's striking here in these examples. And I don't know whether I have another one which kind of highlights this. Maybe again. Yeah, you see this, like you always have ROIs which have this. The second one here is a pretty one, it's a tuned one. The tuning is kind of stable. It even prefers the same orientation, but the response amplitude is clearly, literally just scaled down in block 2. And so that's the most striking feature I took away from this way, looking at the data so far. And overall, these different scatter plots always have the same kind of property in a sense that there's a good fraction of ROIs which lives along the unity line, and then a subset that's clearly changed dramatically. And where they are in space and whether they share functional properties in terms of their preferences, I think that's basically the next stage that we could look into, maybe also combining with what Nicholas has presented.
That makes sense.
Sorry, quick question, understanding wise. If you go to the previous slide, so could you explain again how you normalize? Because I'm trying to wrap my head around. I was thinking about this min-max synchronization.
So it's basically you just get for each orientation the delta F over F. You identify the maximum delta F over F across both tuning blocks, and you not peak normalize to that. And so, for instance, the first ROI has the peak response for 30 degree in tuning block 1. And in tuning block 2, it almost responds as strongly for 30 degree, but everything is related to that peak response in tuning block 1, 30 degree. And so it's a nice way to illustrate these gain changes, right? Because you can scale them, they scale with each other now with this way of normalizing.
So the normalization is just for comparison between ROIs. The conditions are essentially compared in photon space, if you want.
Yeah, so the normalization now is within each ROI, right? So each ROI has a peak response, which is what is basically defining the preferred orientation as a simple proxy. And that's everything is scaled to that one for that given ROI.
Right. That's the same factor you apply to the first block and the second block.
Exactly. Yeah.
Yeah. Okay. Yeah.
You could also peak normalize them individually because you're caring mainly about the shape, but then you don't know whether the response magnitude changes, right? That's
exactly.
And you can still calculate the OSI on the individual traces because the scaling factor doesn't change the tuning bias, right? And so in that sense, it's a good compromise.
Yeah. Agree. Yeah. Thanks.
Quick related technical question. First of all, beautiful analysis also. I find it very interesting. Now, what about, could this be a concern if there's less indicator or less indicator that you can activate over time, that even if you control for the overall F0 reflectivity, you also might expect that there's less of a delta. Does it make sense? So it's overall, there's just less that can activate. So can we really rule out, do we really know that's response magnitude? Can we really rule out that this is just a byproduct of the time passing?
And right now, I would not fully rule it out, but but at least I would say the normalization with the acute F is a good start. And not all of these ROIs have this issue, right? So it doesn't seem like it's a universal bleaching effect. It seems like it's synapse specific, which kind of makes me think it's maybe biology and not just an artifact. But it could be possible that some of this could be still related to bleaching that, I don't know, affects maybe very bright ROIs differently than, like dim ROIs. It's possible.
Yeah, can I comment on this a little bit? I'm speaking through Jerome's microphone, I guess, but I hope everyone can hear me. I think I agree with Sarah that this is promising. We do see bleaching that varies across the dendritic arbor, but it varies in a very specific way, which is that if there's an ROI that's very, very long, the indicator has to diffuse in from the sides. And so you see more bleaching in the center of a long strip that's imaged because the whole long strip is being bleached and the indicator only diffuses in from the ends. So if it is variable bleaching across sites, I would expect to see a pattern where in these very long strips, when you draw out where the ROIs are, in these very long strips, you would see more of this bleaching effect in the center rather than at the edges, and that would tip us off that it might be a bleaching effect. It is in general very difficult to get the F0 exactly right when calculating delta F over F. There is some background light that the detectors get for various reasons. There's fluorescent stuff in the brain, there's excitation that's out of plane, etc. And so knowing exactly what F0 should be in order to compute the fractional change is very hard. And so, yeah, generally as things bleach, the delta F over F as calculated will either drop towards 0, will either vanish, or alternatively, if you over subtract, will become very, very noisy. And so it's very hard to know exactly how to do that right. But the fact that most of the ROIs are stable is promising here. And if it is a variable bleaching effect, I would see that pattern that I just mentioned.
Okay. Maybe I should present the control stimuli that I put on the form. I think it looks like a good time to do that. Okay, so we have 10 minutes left. Let's try to be efficient. So this is the presentation that is linked on the forum. It's a Google slide, so you can go there and edit if you want. I added a first slide to sort of highlight how we have allocated time so far in those SLAP2 experiments. So we see we have, as a we recollect that we have 4 blocks. A first orientation block that is about 7 minutes long, that is doing orientation tuning with shuffle, drifting gratings presentation, and then nullable blocks where we present the same orientation over and over with oddballs that are inserted every 10 or 15 seconds. and then a second orientation block, which is the same as the first one, exactly the same, and then the receptive field block at the end, which are tiny drifting gratings that are moving across the field in XYZ position. The statistics is highlighted in the slides. We have 40 mismatch of each type that are presented, as well as 40 orientations during the orientation block that are presented. So it's sort of match in statistic this way. And for the receptive field, we only present 10 repeats of each combination. So that's where we are located, and already we see effect of bleaching to some extent. So I don't know that we can elongate the session for too much more longer, but this is more or less what we can play with. I can see, so I already foresaw that there were a lot of questions on learning, and so what we could do to control for that. And so I think the feedback that we got is that a control for halt and omission is needed. I think a lot of people have focused on orientation tuning because of that. What does it mean that the elbow block could be triggering any form of learning? So I think we need to control. We might need to control for that. They might be interested in changing the learning context to something that Lucas pointed out. And then what is the statistical power we need for each block? So I think these are open question. And I made several variant proposal here. So the current is at the top. The second one is just hiding the alt and the omission in the shuffle condition, so that just extends slightly the block. So it's not a very painful in terms of time change. The modification number 2 here is where we essentially break the elbow blocks into 2 with multiple orientations, and we have one condition where we just present nothing. So this will be helpful to look at the normal drift of the response, as Casper pointed out. Another proposal here is to break the elbow blocks into 2 subpart, where in one case we actually change the orientation that is being trained. So currently 0 is presented over and over again, and so we could switch to one of the oddball orientation and then put 0 as an oddball orientation, so that you can have controls of the orientation that is being oddball and the orientation that is being trained. And an obvious variant on this is this one, where now we have 2 oddball blocks and an orientation in the middle, and so we essentially sort of controlling onto the effect of the particular presentation that is repeated a lot between orientations. Being able to do this depends a lot on the statistical power and how long we need the elbow block to be. But that's I think what I see the different potential designs. So I'm curious, given the analysis we've seen so far, where do you think the most important control will be?
So it looks to me like mod 4 takes care of everything, right? So that might be the control that makes no compromise. And so one, I agree, power, we should compute and see what works here. One addition there is maybe we should also look into the receptive field block. It might be okay to just do it half as long. The receptive field responses we get are very strong. Maybe we don't need that many trials.
That's possible.
One question: do we need it at all? I haven't seen it in many analyses until now, where it was put to use. I was just wondering, because we know the responses to different orientations or directions, which is probably what we care most about in this particular. Because I was just wondering if we need it at all, because we can see significant responses or not to the stimuli that we provide in the both conditions.
I think it's helpful to know that the location imaging is responsive on the screen, but we could probably make it short enough just to get a population average of all of the ROI? Because I think that's probably possible.
I mean, another thing could be, I'm just not sure whether it's suitable, is to shrink down the stimulus size so that the receptive field mapping becomes actually an internal control for the plasticity, because you could overrepresent the visual stimulus in one particular part of the visual field. And then you could look at the synaptic photons that are not part of that stimulation, right? You see really within that session whether the ones that are presented with a stimulus are subject to plasticity versus the other ones.
I'm not sure I completely understood, Sarah, your point. You want to use the receptive field with us because it's all. Can you repeat?
So you could argue that the receptive field is not interesting if you use a full field stimulus, because it's likely that almost everything will be stimulated.
Yes.
But the receptive field would be interesting if you had a localized stimulus, and then you could present a stimulus in terms of a test orientation block within the spatial position where it was overrepresented versus outside of that position, right? And then the receptive field would be really powerful to look at where the plasticity happens.
Yeah, I mean, that means we will need to have feedback on receptive field mapping to do that, right?
Well, another idea might be, Jerome, to break the receptive field block in half also and start the experiment with one half and end it with the other half. That could also make that more interesting. So we could look at plasticity both for orientation tuning and receptive field location, and then maybe the overlap between those two. Right now with that one block, it's unclear what we're going to do with the data.
I see.
I mean, it's
Lucas,
interesting.
Yes, please.
Just to say, I mean, the work that has been done in the past on dendritic imaging, spine imaging, was focusing on the spatial localization of the inputs, right? So I think it's interesting to have the receptive field of a given input, at least to contextualize it with literally the only kind of evidence that is at a similar scale. And so in that sense, I actually like to have it as a kind of a sanity check even.
So, but if we break it in half, one thing I could imagine is if we look at these synapses that do show a drift in orientation preference, as you two showed, we could see whether their receptive field structure changes, so that if they get inputs from different synapse axon terminals, one might become more dominant. So you could imagine the receptive field structure shifts, as for example, the one that gives the input that is tilted to one direction shifts. In a way, you can think of orientation tuning as MIDI receptive fields, right? So you can think of it as an elongated receptive field. And so if you have, let's say, this orientation input, this orientation input, and one becomes more dominant, it should also in the mini receptive field structure show that there's a shift, let's say in the maximum of the field.
But the mapping is not done to kind of get at that resolution, right? That's the thing.
That's fair. Yeah.
Okay. We're at the hour.
I have a quick question, Jerome.
Yes.
So why do we need? What's the advantage of having two oddball blocks?
It's just you changing the stimulus that is being learned, and this way you can control for if you see the changing responses follow the oddball block, then you know that you're not looking at a natural drift or all other things. So it's an important control.
But I guess that was addressed. If you go back to your previous slide, the mod 2, I thought, is addressing that. Because
mod 2 also do that, but we don't have anything.
Mod 4, I don't see how mod 4 addresses that. For that, we would need two orientation blocks without anything in between.
Because in mod 4, if you see that the learning follow, I think if the learning follow the context, it's a strong indication that the oddball block is the one responsible for the change. If I agree that mod 2 is also insightful, and so this could be two complementary pilot controls.
I guess I'm still not getting what the two blocks of oddball are. They distinct in any ways? Is it to
That's
see?
right. They are distinct. So in one cases, let's say we'll have 0 degree repeated a lot, And the other cases, you had 90 degrees repeated a lot.
I see. And then we want to see. Yeah. Okay. Thanks. I missed that. Thank you.
I had the feeling, since we're like discussing two versions already a bit, that there might be one, let's say, design that is more tailored for addressing the learning question, and then one that might be more tailored to address the contextual modulation of responses, because somehow we see in the current design, we see the two effects overlapping. So there are long-term changes that you can see in the comparison between the orientation block 1 and block 2. But those interfere already with what we see in terms of oddball responses, because the block is so long that already during that period, learning changes might occur and affect the response. So I found that in my analysis that it plays quite a role. So might make sense to actually have two stimulus designs for the two.
So we are at 10. I think it will be really helpful if we do some statistical power analysis. And I think, Lucas, you started this. Do you think you could present that next week?
Yes. It's just I need a bit of feedback. I feel, because like the statistical power analysis, in that sense, it's always tied to a specific test or a specific statistic analysis that you do. And I was wondering, so right now I have an analysis comparing population averages, which have a very different trial requirement that, for example, focusing on individual ROIs. And yeah, it's I'm not really sure if we will get a really quantitative statement for these ROI specific measures, because I would expect it depends very much on the analysis that we do in the end.
That's right. But could you collaborate with Nicholas and Sarah, and just so that we have I feel like it would be helpful if we have a I mean, I think, for instance, you could do the measurements on the OSI to know how well you measure the OSI depending on number of trials. And I think Nicholas would just point out at different metrics, how well can he characterize those sub ROI that have strong change. And so I feel like the number of trials, I think I'm guessing that Nicholas will have constraint on the orientation block, right? And so I just feel like we need to have a sense of how long the orientation block needs to be, and maybe the elbow blocks as well. And so
yeah,
could we have a discussion next week on that?
Definitely, yeah. Let's see what we have in terms of analysis of that. If someone wants to collaborate on the subsampling and comparing the analysis, then reach out. But also, it might be that we have to rely a bit on gut feeling, to be honest, when discussing this as well. Just so that to manage expectations, that it might be difficult to really pinpoint. This is the trial number we need.
Yeah. I wonder. I'm going to talk with Casper on whether we could.
And I suppose in the discussion thread we can talk a little bit more about what you mean by subsampling. And I think I have an idea of what you mean, but I need to look into that. I'm speaking of the relation between subsampling and determining the right number of trials to ensure that, say, you have an accurate estimate of, say, the mean responsiveness of an ROI to a specific orientation.
That's right.
Because the question, I suppose, is how reliable is that mean response?
Can I ask a quick question? So just for curiosity, Lucas, I understand the need to have basically a second oddball block to make the deviant also a reference signal, right, based on the analysis that you want. What if you just try to take the current oddball and divide the numbers in half, pretending like you split it in two, and see how well can you still capture the mismatch responses, for instance? Because then at least we would know if we could divide that one current oddball into two. And as long as there's something overrepresented in one oddball and the other, it could still be contextualized in terms of plasticity of orientation tuning, right? You just might have now different prediction because you're not presenting only one stimulus over and over again, but mainly two. But it might be good proxy to just find out if dividing the odd block into two would be good enough.
Yeah, I did this analysis already, but as I said, it's the learning effect kicks in also if you I mean you really see how it kicks in if you split it, because you really see a difference if you compare to the first and the second oddball block. But yeah, in terms of statistical power and so on, yeah, we need the single ROI analysis still to make a statement about that. Yeah.
Wouldn't characterizing the variability of the mean responsiveness of the ROIs to these different orientation tunings or directional tunings, wouldn't that be very critical for all this? Because if the variability is very low, then we would expect the mean to be more reliable. If the variability is very high, then we would expect that we would need more trials, I would think.
Yeah, for sure. It's I mean, maybe we should have a schedule like a separate meeting in like before next meeting, maybe in the discussion of exactly this point of this meeting, because I have a bit of a post there already. We could maybe you could comment there and we schedule a meeting there somehow, and then we can discuss and see how we prepare the next meeting.
Okay,
that sounds fine.
So we'll continue discussion on statistic in the thread, and Lucas can lead the discussion, but it might need contribution from multiple people next week. And I'm gonna present the overall session type design again, and let's have a discussion about how we want to leverage what we've learned so far on the full session type, because I feel like that's the right time now to do this, because we are getting ready and pushing this to bonsai, and so let's do that. Okay, so we'll continue to talk on the forum. Thanks everyone for preparing so many fantastic analysis. It was really fun.
Have a good day. Bye.
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 Thank you.